So let's talk through an algorithm. So if you want to compute inverse sine of the sine of alpha, well, let's write down what that would mean up here. So if you want to compute the inverse sine of the sine of some quantity alpha, you should get some angle theta back. Now let's try to rewrite what this should mean. This will mean let's color code a little bit. That means the sine of theta should be whatever is inside of those parentheses. And so we need to satisfy those two conditions. So let's do it just one at a time. If, yeah.
Do you have any more packets?
For this time or from last time? I do not. So let's carry on from here. So can you think of some angle, some choice of theta which solves this equation? Well, how about alpha? If theta were equal to alpha, would this equation be true? So there's a first guess. Let's find some angle theta for which sine of theta is the same as the sine of alpha. So let's just try theta equals alpha. And I think as I do that, I'll try to compute the inverse sine of the sine of 61 pi over 6 right here as we do it. So our first guess will be 61 pi over 6. There's an initial guess. Well, we need this angle theta to be in the interval from negative pi over 2 to pi over 2. Is that number 61 pi over 6 in between negative pi over 2 and pi over 2?
No.
No. So the first thing that I'll try to do, so if it were already between negative pi over 2 and pi over 2, you would be done. You would satisfy both of these conditions. We don't. So the first thing that we'll try to do is we'll say, well, that number is like off of an acceptable answer by some rotations by 2 pi radians, some full revolutions. So we can throw out full revolutions. And we'll aim to throw out full revolutions until we get something between negative pi over 2. And we would like a pi over 2 to be there, right? If we could get it between negative pi over 2 and pi over 2, we would be done. But if we're just going to use full revolutions, we can just get it to be between negative pi over 2 and negative pi over 2 plus 2 pi. So first we'll try to get it between negative pi over 2 and 3 pi over 2 by throwing out some excess multiples of 2 pi. So let's do that with 61 pi over 6. Let's see. You could rewrite that as like, well, that's a really easy bit of division to do, right? 61 divided by 6 is 10 plus a sixth. So there's 10 pi plus pi over 6. Is there a multiple of 2 pi that you could subtract to simplify that? How about 10 pi? Yes. That's 5 times 2 pi. So it's a multiple of 2 pi. So throw that out. Get a second guess. So there's the result of step 2. Throw out some multiples of 2 pi until you get between these two numbers. If your angle is now actually in the correct range, that is negative pi over 2 to pi over 2, then you're done. Is this number between negative pi over 2 and pi over 2?
Yes.
So we're already done. We don't need to do step 3, whatever it is. And we get that the inverse sine of the sine of 61 pi over 6 is pi over 6. But it might not work out that way, right? You might be off, right? You might wind up, right? The range of inverse sine is, you should think of it as being quadrant 4 and quadrant 1. What if you wind up in quadrant 2 or quadrant 3? Then you would want to like reflect over the y-axis. But we know a rotational thing that does that. If you replace an angle by pi minus that angle, you get into quadrant 1 or quadrant 2. Quadrant 1 or quadrant 4. So, step 3, if your angle is now actually between negative pi over 2 and pi over 2, you're done, which happened in this case. Otherwise, replace that angle by pi minus that angle. And in order to see that happen, let's try to do it exactly in this case. So let's try to compute the inverse sine, or arc sine, of the sine of 67 pi over 6. So what's the initial guess you would want to make for what the inverse sine of the sine of 67 pi over 6 is? 67 pi over 6. There's an initial guess. Is that number between negative pi over 2 and pi over 2? No, because 67 over 6 is bigger than 11. So first, let's figure out how to rewrite this so we see a bunch of even multiples of some multiples of 2 pi that we can throw out. How could you rewrite 67 pi over 6 so you see that? If you like, what's the result of doing division? Yeah.
10 pi plus 7 pi over 6.
10 pi plus 7 pi over 6. How many people instead wrote that as 11 pi plus pi over 6? You're also correct. Those are both the same thing. But in 11 pi plus pi over 6, do you actually see the multiple of 2 pi you need to throw out? No, I guess not. In the first one, you do that. So let's throw out, I mean, either way, you kind of do, right? What's an even number that's pretty close to 11? Well, 10. So it's not so bad. So let's throw out that 10 pi and see what we're left with. So here's our second guess. Seven pi over 6. And let's just make sure that we at least that we actually satisfy what we need to in this step 2. Is that number between negative pi over 2 and 3 pi over 2? Let's see, 7 pi over 6. That's just like a little bit bigger than pi. And you want to see how that compares with, well, is it bigger than negative pi over 2? Yes, it's positive, right? So it's bigger than negative pi over 2. Is it less than 3 pi over 2? It is, right? Because 3 pi over 2 is 3/4 of a revolution. That's less than 3/4 of a revolution, so there you geometrically see it. So it's actually in the right range to be our second try. So our second guess is actually 7 pi over 6. But is this angle 7 pi over 6? Is it between negative pi over 2 and pi over 2?
No.
No. So we need to reflect it over the y-axis. And when we reflect it over the y-axis, we'll replace 7 pi over 6 with pi minus 7 pi over 6. So our third guess, I guess this will be like our final guess. Pi minus 7 pi over 6. What's pi minus 7 pi over 6? Negative pi over 6. So the final answer, the inverse sine of the sine of 67 pi over 6 is negative pi over 6. How do people feel about that? That seem okay? And I guess there's ultimately one thing you can always do to check these. I probably should have had this pulled up already. And yes, it's silly to do a Google search for Google, but that's just what I just did. So arc sine of the sine of 67 times pi over 6. Oh yeah, so it'll give a decimal approximation. So it's negative and pi is somewhere around 3. Yeah, that looks like it's somewhere around negative pi over 6. Yeah. So I think I believe the answer. People feel pretty good about this? Do you think that there's a similar algorithm for cosine?
Probably.
Chances are. Let's talk through it. So if you want to compute the inverse cosine of the cosine of some number alpha, your first guess should be theta equals alpha. If that's already in, oh, you can't actually see that. If that angle theta is already in between 0 and pi, then you're done. But chances are it won't be. Or maybe it will be. Maybe that would be a fine question to ask too. If it's not, then you need to do some work. So the first thing I'll suggest is start throwing out multiples of 2 pi, and I'll even state as the goal get between negative pi and positive pi. Really, you can get between any two multiples, any two things that differ by 2 pi. I'll suggest this one for a strategic reason. And then step 3, if your final angle is in between 0 and pi, then you're done. Otherwise, well, your angle is negative instead of positive, but negative signs don't change cosine, so just take that angle and make it positive. So let's try to run that algorithm for these examples. So let's try to compute the inverse cosine of the cosine of 61 pi over 6. So what should be your first guess? What should be your first guess as the inverse cosine of the cosine of 61 pi over 6? 61 pi over 6. And let's rewrite that so that we see a multiple of 2 pi somewhere in there. 61 pi over 6, that's the same thing as, yeah, just say it loud enough. 10 pi plus another pi over 6. I couldn't actually read lips, but I think I saw you say the word pi silently. And so I figured you probably had that. And there's a multiple of 2 pi we can throw out there. 10 pi is a multiple of 2 pi. So our second guess will just be pi over 6. So let's see. There's the result of step 2. Is that angle now between 0 and pi? It is. So well done. So the inverse cosine with cosine of 61 pi over 6 is pi over 6. Let's try it also with 67 pi over 6. So step 1, we write it so that we see a multiple of 2 pi. So what's a multiple of 2 pi that's pretty close to 67 pi over 6? Maybe the better question is, how would you actually want to rewrite that?
10 pi over 6 plus 7 pi over 6.
Yeah. So the first, oh. I see a multiple of 2 pi to throw out, so gesundheit. And let's just do a quick check. 7 pi over 6, is that number between negative pi and positive pi? Careful. Yeah, 7 6 is a little bit bigger than 1, so that's no good. So I'm actually going to subtract another 2 pi. Let's see, 2 pi is the same thing as 12 pi over 6. So that'll result in, I guess, an angle of negative 5 pi over 6. Is that number now between negative pi and positive pi? And that's all we ask for in step 2. So there's our second guess. Negative 5 pi over 6, is that in between 0 and pi? No. But how can we turn it into something that is between 0 and pi? Let's take another negative sign in front, because that'll cancel the negative sign we already have. So the final answer will be negative 5 pi over 6, also known as just 5 pi over 6. So the inverse cosine of 67 pi over 6 I see now as 5 pi over 6. Shall we do a quick computation to check? And, I mean, maybe you guys have calculators that allow for symbolic outputs, but I'm just going to use the Google calculator. Arc cosine of the cosine of 67 pi over 6. And I think that the answer should be 5 pi over 6. And in order to check that, if it's actually 5 pi over 6, then subtracting 5 pi over 6 should result in 0. Oh. Do I need extra parentheses? Yeah, sure. That shouldn't be too complicated for Google to do. All right. And now to compare. About the same? Cool. So I think I believe it now. People have any questions about that before I move on? Cool. So let's start it on something new. So we've talked about inverse sine and inverse cosine. There are like four other trig functions we can try to invert. Secant and cosecant. Maybe I won't bother with those because those are just like 1 over sine and 1 over cosine. And then there's tangent and cotangent, but those are also just reciprocals of each other. So I'll just think about inverse tangent. If I know inverse tangent, that's probably enough to solve any trig equation you come across. And let's try to do it really super quickly. Let's start with the graph of tangent of x. So the tangent of x goes to the point 0, 0. Tangent of 0 is 0. It has a vertical asymptote at pi over 2. And a vertical asymptote at negative pi over 2. And then it just repeats. It's pi periodic, and there's an interval of length pi. People feel pretty good about that? Like that's the graph of tangent. So step 1 in graphing the inverse sine and inverse cosine was find it, well, let's answer this easy question first. Is that function actually 1-to-1? Does it pass the horizontal line test?
No.
No, it fails it very badly. Every horizontal line is intersected infinitely many times. But we can restrict the domain, just like we do with x squared to get square root of x. Let's find the biggest domain we can on which this function is 1-to-1. So starting at x equals 0, how far to the right can you go before something bad happens? Pi over 2, where I guess the vertical asymptote is something bad. How far to the left can you go before you see something bad happens? Negative pi over 2, which happily I've already graphed in purple. Is this function 1-to-1? No. Is there a restricted domain containing 0 on which it is 1-to-1? Yeah. Negative pi over 2 to pi over 2. Should I include the endpoints? Why not?
They're asymptotes.
There's a vertical asymptote there, so those are definitely excluded. So I'm only going to take this purple piece of the graph when I invert it. So here's the definition. The arctangent, or inverse tangent, is the inverse to the function tangent of x after its domain has been restricted to negative pi over 2 to pi over 2. Nice. So let's try to graph this thing. So I see in purple that tangent goes through the point 0, 0. So what's a point that inverse tangent should go through? 0, 0. Great. I see, let's see, it's increasing, so it will also be increasing as an inverse function. I see a vertical asymptote at x equals pi over 2. When you take the inverse function, the vertical asymptote isn't going to stay a vertical asymptote, so it becomes something else. Horizontal. It will become a horizontal asymptote. Right? If you take a vertical line and change the job of x and y, it becomes a horizontal line. So you'll see a horizontal asymptote at y equals pi over 2. You'll see a horizontal asymptote at y equals negative pi over 2. There you go. People feel pretty good about this? So let's compute some things from this. Just by looking at this graph, what's the domain of that function? All real numbers, negative infinity to infinity. Take your pick. What is the range of that function?
Negative pi over 2 to pi over 2, non-inclusive.
Negative pi over 2 to pi over 2, excluding the endpoints. So just summarizing all of these things. And sorry, if you wanted to, you could now repeat all of last time's lecture for this function. I think I just won't in the interest of time. So inverse sine, we've already computed that. That has range negative pi over 2 to pi over 2, inclusive, and domain negative 1 to positive 1. Inverse cosine has range 0 to pi, and domain negative 1 to positive 1. Inverse tangent has range, someone said all real numbers earlier, so I'll write down the symbol for all real numbers this time. You could also write down negative infinity to infinity, right? That's the same thing. And it has, Chris, that was the domain, not the range. Nobody stopped me.
I was scared.
I know, I'm too intimidating. I know I make so few mistakes, it's confusing when I make a single one even. So this thing has domain, all real numbers, and it has range. I picked a great time to not be using the erasable pens. Negative pi over 2 to pi over 2. Are the other ones screwed up? No, those are actually the range. And if you take a number for which inverse sine of x can actually be computed, what's the sine of the inverse sine of x? As long as it's actually defined. You can't take the sine of the inverse sine of 17. What about the cosine of the inverse cosine of x? That's also equal to x. What do you think the tangent of the inverse tangent of x should always be? X. And that'll be true as long as you're in the domain of inverse tangent. But what's the domain of inverse tangents? All real numbers. So there is in fact no constraint. The tangent of the inverse tangent of a number is always that same number you start with. So what I'd like to do today, and maybe this will take us into a middle, most probably will, is let's see what happens when we mix an inverse trig function with a trig function, but not the same ones. Let's try to see what happens when we evaluate the sine of the inverse cosine of a number. And let's see, how many people, just by previous experience, already know what the answer is going to be? Okay, good. It won't be a hard answer, but it'll be, I think, illuminating to see it without already knowing what it will be. So let's start with even just a single example. So I'm going to compute two different ways the cosine of the inverse sine of 3/5. And then I'll try to get just a general formula. I'll try to compute the cosine of the inverse sine of some number x. And the two strategies that I'll use are purely algebraic and purely geometric. And I mean, I guess I'll leave it up to you guys. What would you guys rather see first, the geometry or the algebra? How many people would rather see geometry first? How many people would rather see algebra first? Okay. I guess all things being the same, there's not a dependence either way. Cool, so here's what we'll do. So I'll go ahead and let theta be the inverse sine of 3/5. So what is the goal? The goal is to compute the cosine of theta. But that's too hard all at once. I definitely know one thing though. If theta is the inverse sine of 3/5, then what is the sine of theta? 3/5. Right. When you say theta is the inverse sine of 3/5, you are saying sine of theta is equal to 3/5. And you're also saying that it's in a particular range. Oh, cool. So what this is saying is if I tell you I have an angle whose sine is 3/5, then what's the cosine? We've done that before. Oh yeah, so I guess like we've done literally that problem before and we got 4/5. So either just by memory we know the answer should be like 4/5. Well, maybe we know it'll be plus or minus 4/5 right now. And we'll deal with the plus or minus. It is the plus is the right choice. Let's go through the walk. So let's see. You need two pieces of information if you want to compute cosine. If you know what sine is, you're almost done. You might be off by a plus or minus sign. You also need to know like what quadrant it lives in. What quadrant does it live in? What's the range of inverse sine? Quadrant 1 or quadrant 4. But if sine is positive, is it quadrant 1 or is it quadrant 4?
1.
Quadrant 1. In fact, that doesn't matter, but it's a good observation to make. In either quadrant 1 or quadrant 4, is cosine positive or negative? Positive. So cosine should be positive. And now what do? If you know sine, you would like to know cosine. Well, you have an identity that relates them. Cosine squared plus sine squared is always 1. So maybe I'll be lazy. I'll replace the cosine with a c. Plus, we know what sine is. It's 3/5 squared. That'll equal 1. And in some sense, we already know what the answer is. It should be 4/5. But if you go and solve that for c, I mean, how many people want me to go through the algebra? Okay, then I will do if you have already done it. So let's see, 3/5 squared is the same thing as 9/25. So let's do that. This becomes cosine squared plus 9/25 is equal to 1, which I'll rewrite as 25/25. You want to solve this for cosine, so let's subtract the 9/25 over to the other side. I've already arranged a common denominator, so the subtraction will be easy. We'll get cosine squared is equal to 25 minus 9 all over 25, also known as 16/25. That okay? And now I just need to take the square root of both sides. So cosine should be plus or minus the square root of 16/25. And let's do it one step at a time. Is cosine positive or negative? Positive. So because of this constraint, I'm going to take the positive choice. Do you see any perfect squares under that square root? Do you see only perfect squares under that square root? What's the square root of 16? What's the square root of 25? 5. And I guess this we've already dealt with. How do people feel about that? Does that seem like something we could have done for basically any starting number? And we will. We'll get a general formula at the bottom of the page. But before we do that, I think I would like to do the same thing from right triangle's point of view. So let's do this this way. So again, I'll let theta be the inverse sine of 3/5. So then sine of theta is equal to 3/5, and this number should be in quadrant 1. In quadrant 1, there's no worry about positivity, negativity. You can just draw a right triangle and see what happens. So if sine is 3/5, then you can draw a right triangle, and I mean, so you know that opposite over hypotenuse should be 3/5. And these things are scale independent. So opposite will be 3, hypotenuse will be 5? Yeah. For this one? It would have been quadrant 4 if this were like a negative 3/5. Right, quadrant 4. Ooh, sorry, wrong. Yeah, quadrant 1. Okay, yeah, sorry, I didn't hear you when you asked. I heard, isn't it in quadrant 4, which is the opposite of what you went twice. Yeah. So secretly, it's not in quadrant 4, but that's not actually relevant to the computation. In quadrant 4, cosine would still be positive. And that'll be relevant when we do the general computation. Cool. We can also fill in this triangle with different choices of numbers, right? That 3/5 is maybe convenient, but this could also be, if you wanted 1 and 3/5 if you wanted it to be. Maybe it's nice to have as nice numbers as possible. If you like, I'm just leading up to what the general computation will be. So there's a right triangle, and I would like to compute cosine of theta. Cosine is adjacent over hypotenuse, so if I can figure out the adjacent side, then I win. So there's the adjacent side. So apparently, I can solve for that by using the Pythagorean identity. The adjacent side squared plus the opposite side squared should be the hypotenuse squared. And if you take that and you solve it for the adjacent side, what do you get? Well, really plus or minus 4, but we know that the answer should be in quadrant 1, so it'll be positive. Cool, so that means that the adjacent side length is 4, so what's the cosine of theta? So that means the cosine of the inverse sine of 3/5 is 4/5. Happily, we got the same answer as we did the first time around. How do people feel about that strategy? Good. Maybe I'll give you one piece of advice. When you wind up with numbers that are negative, sometimes thinking about right triangles can get off-putting. So you do have to worry about whether you're actually in the correct quadrant. I would definitely believe this number up to a plus or minus sign. But you already know the answer should be in quadrant 1, so you know it should have a positive sign. Let's try to do the general computation. Let's try to get a formula. Let's try to compute the cosine of the inverse sine of an arbitrary number x. And we have enough time to do it both ways, either by the algebra or by the geometry. Maybe I'll do the same as I did with 3/5 and do it by the algebra and then use geometry. So let's try the algebra first. Let's let theta be the inverse sine of x. Then what can you tell me about the sine of theta? Yeah, let's just say that.
X.
It's x. And maybe I'll also add this. What quadrant should that angle be in? What's the range of inverse sine?
It's 1 or 4.
Quadrant 1 or quadrant 4. And you can't tell, right? I don't know if x is positive or negative.
Perfect.
But that's kind of okay, right? In quadrant 1 and in quadrant 4, is cosine positive or negative? Positive. So it doesn't matter which. We'll be okay. So the payoff here is either way, cosine will be positive. Nice. So now let's use the Pythagorean identity and work it out. So I know that sine squared plus cosine squared is always equal to 1. So I'll rewrite cosine as just c. C squared plus, what's the sine of theta equal to?
X.
X. And x is like the variable in the problem, so that's an okay thing to have. Question? Okay. Does that look like we could solve that for c? Yeah, I guess it's even like easier than before because there's no simplification to do. Just subtract the x squared and then take a square root. So apparently, cosine will be plus or minus the square root of 1 minus x squared, but will it be positive or negative? Positive. So the cosine of the inverse sine of x is always equal to the square root of 1 minus x squared. That gives us one of the formulas promised on the first page. So I'll go back to the first page and fill that in. The sine of the inverse, nope. The cosine of the inverse sine of any number x is the square root of 1 minus x squared. Cool. Would you like to see the same argument from the point of view of geometry? So let's try to encode this information as a right triangle. So I know that the sine of theta is x over 1. So I could draw that as a right triangle. That would mean that I have some angle theta. And you can build a right triangle starting with that angle theta where the hypotenuse is 1 and the opposite side is x, because sine is opposite over hypotenuse. And maybe you notice I drew that line, the x line going up. So I've assumed here that sine is positive. Maybe I'll draw a second version of it. X might be negative. Either way, do you think we could figure out what the adjacent side of this triangle is? Yeah, you would have to solve, well, I guess, opposite squared plus unknown squared is equal to 1. And, I mean, it's the same algebra as you literally just did. So, this adjacent side is the square root of 1 minus x squared. The hypotenuse is length 1, so cosine is this divided by 1. We get the same answer. Cool. And in the interest of time, I think I'll close with just one last thing. In fact, maybe I'll just. I think I'll just give this formula. We'll notice that it's an interesting looking formula. So the formula that we'll get if we try to compute the sine of the inverse cosine of any number x. Any guesses for what we might get? You get literally the same thing. So I'll write down that formula. What I'll encourage you guys to do is, before next class, is think about some of the things on this page. It'll be literally the same walk as on the previous page, but with sine and cosine flipped. Right, the walk you need to do if you know sine to find cosine is the same as the walk you need to do if you know cosine and want to find sine. So I'll put this down. And I see people are putting things away, but my intention in skipping this computation was getting to one other example in these notes. Let's try to do something. So one can get a formula for things like the cosine of the inverse tangent of an arbitrary number x. And in fact, if you look in the relevant section of the book, you will see all of these formulas. But I will encourage you maybe to just know the formulas for inverse sine of cosine and the sine of the ones that we've got so far. Memorize those ones. And instead, let's think about how you can figure out what the cosine of the tangent of 4/5 is, instead of memorizing a formula. And let's try to do it using the point of view of triangles. So let's let theta be the inverse tangent of 4/5. So that means the tangent of theta is the same as the tangent of the inverse tangent of 4/5, which is always 4/5. So that means the sine theta over cosine theta is 4/5. And you could do algebra from there to walk it out, but maybe I'll instead draw this as a right triangle. In terms of SOHCAHTOA, tangent of theta is opposite over adjacent. So let's draw this as a triangle. So you see this angle theta. So you can make a right triangle out of this, where the opposite is 4, the adjacent is 5. Out of that picture, do you think you could figure out the hypotenuse? All right, the length of the square of the hypotenuse, the square of the length of the hypotenuse is the sum of the squares of the remaining two angles, if you happen to have a right triangle. So the hypotenuse squared is 4 squared plus 5 squared. 16 plus 25, I think that's 41. Did I screw up my arithmetic? Cool. So the hypotenuse squared is 41. So how long should the hypotenuse be? Square root of 41. There's not a perfect square in there. Aha. But I now want to compute the cosine of theta. In terms of a right triangle, what's the cosine of theta? SOHCAHTOA adjacent over hypotenuse. So the cosine will be adjacent 5 over hypotenuse root 41. And the only change that I'll make, because I have 20 seconds, is I shouldn't have a square root in the denominator. So multiply and divide by root 41 to get 5 root 41 over 41. How do people feel about that? Does that seem okay? And one could replace all of this work using right triangles with instead stuff involving just algebra. Cool. So let's see. Think about some of this stuff, and especially the stuff on the page that I more or less skipped. Try to think about those ideas. Let's talk about them. We can come next time. I have another one. If you already, so if I still have your attention, if you look on these rolls.
Oh, yes, and I turned in my.
Okay. Yeah.
We didn't have to do this because it was between negative pi and 3 pi over 2, right? So that's, this one was not between negative pi and 3 pi over 2. So that's why we had to add this in order to make sure it was then between the negative pi and pi over 2, which it was. So that was our answer.
Okay, so step 3. So in step 2, you want to get it to be between negative pi over 2 and pi over 2.
Not negative pi over 2 and 3 pi over 2?
No, sorry, instead, you were right for step 2.
That's step 2, right?
And this number, 7 pi over 6, is between negative pi over 2 and 3 pi over 2. So that.
So then why did we change it down here?
So in step 3, if your angle is now between negative pi over 2 and plus pi over 2, so you notice that's slightly different, then you're already done. But is 7 pi over 6, is this between negative pi over 2 and plus pi over 2? So that's why step 3 had to happen.
This one is between this one is between
Okay, so this is between negative pi over 2 and 2 pi over 2. So we'll leave it for step 2. Now let's go to step 3. Step 3 is your angle between negative pi over 2 and plus pi over 2.
No. Okay, thank you.
So that's what you need to do.
Thursday, can I get it?
Yeah, it's upstairs. Have you already looked at your score in D12?
Yes.
Did you turn in a sample for it? Is your score such that you can turn in a sample?
Yes.
Oh, okay.
I didn't realize that we were receiving the packet. I do have
Okay, well, do you have the sample done? Okay.
waiting to see you guys.
Okay. So since today's the day that I wanted to collect it and it's written on the sample, ooh,